here are some particular n by n matrices with certain condition on the entries. And moreover, it is known that this is non-empty if and only if B is less than or equal to W, and so you'll see this appear in the last class. And okay, some special cases which you're probably familiar with of these are the Grassmannians, as well as Schubert varieties, and perhaps also positroid varieties. And just one last piece of information is that these Richardson varieties themselves are a special case of something called break varieties. Okay, so that's my little introduction to Richardson varieties. And so if you know more, that these are defined as the intersection of the Schubert cell together with the opposite Schubert cell. All right, so some history and then motivation. Okay, so we'll mostly be concerning with not the Richardson varieties themselves, but rather the coordinate range of the Richardson varieties. And the story starts for us with the work of Leclerc, who constructs cluster subalgebra. Okay, so I have a cluster algebra here, A, and it is determined by an initial seed sigma, and I'm going to put a superscript back for Leclerc. It depends on E and W, and so W underlined for me is the choice of a reduced expression for W, and so this is an initial seed for cluster algebra, and then you can use the machinery of cluster algebras to generate the entire cluster algebra from this initial data, and so what he shows that this lies inside the coordinate ring of the Richardson variety. And really, he uses categorification to do this. And so perhaps it is not, it is explicit, but you need some work in order to see what this seed actually looks like. And we'll do an example, so you'll see. And then the main conjecture that we'll be talking about today is that actually, well, this is not a containment, but the two are equal. So the coordinate range of the Richardson variety actually is a cluster algebra starting with this initial seed of Leclerc. Okay. Let's do some fixing. Okay, and so the story continues with the work of Menard. Okay, so Menard, who was a student of Leclerc, he comes up with yet another construction. So he constructs a different seed, let's say, straight down, also starting from a choice of a reduced expression for W, and which also lies inside of the coordinate rate of the Richardson variety. But the process, the construction here is quite different from the one here, and so it is not exactly clear how the two are related. Most of them also use categorification, but the interesting thing here is here you actually start with the seed of Leclerc, where B is actually the identity permutation, and then there's an algorithm, a sequence of mutations and vertex deletions that lets you then construct a seed of NR. But it is not clear then how these two are related. But then there was a subsequent work of John Keller, where they show that actually, if you look at the upper cluster algebra generated by Menard's seed, this actually agrees with the coordinate range of the Richardson variety. So now the Richardson variety is now the upper cluster algebra here. And so in general, it is known that the cluster algebra is contained inside the upper one, but the two may not necessarily be equal. Okay. And then comes the work of Ingermanson. Okay. And so she constructs yet another seed, very different now from the previous approaches. And she also shows that the upper cluster algebra generated by her seed also agrees with the coordinate ring of the Richardson variety. But again, it is not clear how all of these three now seeds are still related. Okay. And then the last work I want to mention is actually a sequence, works of two groups of people. One of Casals, Gorski, and Simental, as well as another work of Lashin, Lamb, Sherman Bennett, Spire. So these are very recent, maybe 2020, 2021, perhaps, even 22. So what these do, so they're independent works, but what they do is they construct cluster algebras for braid varieties, or coordinate rings of braid varieties. And on the what I raised just here is that Richardson varieties are a special case of braid varieties, and then it follows that the special case of the first construction is you get Menard seeds, and the special case of the second construction, you get Ingermanson seed. Again, it is not clear how the two are related. But the interesting thing here is that following the second paper is they actually show that if you look now at just the cluster algebra, starting with Ingermanson seed, this actually is the coordinate ring of the Richardson variety. Okay, so this is an improvement of Ingermanson's result, right? We can remove the upper cluster algebra condition and get the actual cluster algebra here. All right, and they're now, okay. Ready to state the result. That's our contribution with Melissa, and as well, we can get Leclerc's conjecture type. So the cluster algebra generated by Leclerc seed equals the coordinate ring Richardson variety, and moreover, we have the following. So first, it looks like the cluster algebra is determined with this initial seed, and the initial seed depends on the choice of the reduced expression of W, and we can show that actually the cluster algebra doesn't depend on the choice of the reduced expression, meaning for different reduced expressions of W, you would get seeds that are related to each other by mutations. So you get the same cluster algebra. So cluster algebra is independent of choice of the reduced expression W. And then the second piece is actually, so this is how our proof goes, but then sort of this is a nice observation, is that actually the two seeds, Leclerc's and Ingermanson's, are related by something called the twist map. Twist map of Gaussian. So meaning that this, well, you'll see the two seeds are really, they have the same combinatorics, pretty much. The quiver is the same. The cluster variables are different as functions on the coordinate ring, but they are related by this particular automorphism of the Richardson ring. Okay, so sort of this is an overview and sort of how this all fits. Now let me tell you more about sort of the ingredients that go into the proof and what these things actually look like. So let's start with Leclerc's construction. All right. So suppose lambda is going to be now a pre-projective algebra. I'll do some representation theory of type A. And so just a reminder, the algebra is quiver looks like this. And actually, if I took my representation C and that would be an Sn, then the algebra I would consider should be on n-1 vertices. Call these x's and call these y's. Then the relations are, let's say, xy equals yx. And so what this means, if I look at this vertex which is not on the end, if I apply x and y, it should be the same as doing yx on the other side. And if I'm at the end, this means that xy, well, there's nothing on this side, so this would be 0. Okay, so that's the relations. And so what do we do here? So the theorem of Leclerc is he constructs this subcategory CBW inside of the module category of lambda, which is has a cluster structure, cluster category, in the sense of one large finely corrected Todorov. So you already see this in Q's talk, with cluster character. Okay, so cluster character is just a map which goes from the cluster category, in this case, to the coordinate ring of the Richardson variety. And what it does is it sends objects in here to some elements of the coordinate ring, and in such a way, well, that reachable, indecomposable rigid object here going to correspond to cluster variables on the other side. And okay, so this tells you that there is this cluster structure inside of there. Now, how do we get this initial seed? is, okay, so this is continuation of the theorem. Moreover, there is this object, U, VW, inside of cluster category, which is a cluster building object. And so this cluster tilting object induces the initial cluster sigma. So the sigma that we saw before. Okay, so what is this? So if you apply this cluster character map to this object, you get elements of the coordinate ring, and these would be exactly the initial cluster variables. So if you do this, you get initial set cluster variables. So in general, this object is not necessarily basic, but sort of, okay, you remove multiplicities and you write them out and you get the initial cluster variables. And then, well, another piece of information which determines the seed is the quiver, and the quiver is the endomorphism quiver of the cluster building object. And then we will take basic, so we remove the repeated signs. Okay, so this is the seed of Leclerc. And so, okay, I should say, so this is the quiver. And so, sort of the whole difficulty in understanding Leclerc's initial seed or Leclerc's or this cluster algebra is to get a more explicit understanding of both the cluster variables as well as the initial quiver. Because it is really defined sort of recursively, and if you wanted to have a more concrete definition construction. Okay, so now I want to give you an example of how one would calculate this without sort of giving you all the details. Hopefully you'll see how it works. All right, so let's choose a W, reduce the expression to W, and it's going to be the same ones on that side. S3, S2, S1, 4, 3, 2, 3, 4, and my B is going to be S3. Okay, S3 is certainly less than or equal to W, so that's good. And what happens, so the first thing is once you have your B and W, is you want to find an expression for B inside of W, which is rightmost. Okay, so in this case it is simple. You look at, this is just S3, and I look at the rightmost S3, and I'm going to underline it to denote that this is how my B appears inside of W. Okay, here N is 5. Okay, so what happens next is each of these, I'm going to label these transpositions 1, 2, 3, 4, 5, 6, 7, 8. Index. And so each of these i's, I'm going to give you a module x of I. And so the way I'm going to think about this module, so in Leclerc, if you read the paper, so you choose a transposition, let's say this one, and then you're going to build recursively a module Qi according to the transpositions which appear to the right. And so there's a sequence of functors you can apply to. In this case, this will be an injective module in 3, which first builds up a submodule of the injective, and then it's going to take a quotient of what you get. So this is very sort of functorial, but in type A, I'm going to give you a simplified version and sort of convert it more into the combinatorics. Okay, so in type A, this you can write as U sub 2 sets, I, and J, so these I, J, these are particular subsets of N. And I'm going to tell you later how to calculate these. And the nice thing is now if you apply this cluster character to this module, what you get is a very, very nice function on the coordinate plane of the Richardson variety, the coordinate plane of the Richardson variety. I'll just put a Leclerc here, which is just a minor, so it's going to take a determinant on columns II and columns indexed by this set and rows indexed by this set and columns indexed by that set. Okay, so it's a very nice function inside of the coordinate. Okay, so let's do further example with this. What the modules look like. Okay, so if I link this game to the index 5, okay, as I said, I'm not gonna tell you at this point how to get the sets, but in a second we'll know. So this II and this IJ are 1, 2, 4, and 1, 3, 5. Okay, and how can now, given this, how can I interpret this as a module? So what you do is you look at this grid. Okay, 1, 2, 3, 4, 5. And each of these is going to give me a lattice path from northeast corner whose vertical steps are 2 lattice path, or 1, 2, 4, and 1, 3. Okay, so let me just give an example here. This is very nice. So I look at this 1, 2, 4, and I want a lattice path starting here with vertical steps. I'll have labels 1, 2, and 4. So my first step should be vertical. My second step should be vertical. 3 is not here, so it's horizontal. 4 is vertical, and the rest are horizontal. So this is my lattice path. And I can do the same with 1 through 5. I will have 1 here, 2 is horizontal, 3 should be vertical, 4 is horizontal, 5 is vertical, the rest are horizontal. Okay, and so it will always happen that 1 is below the other, the 1 to 4 will be below, the second one will be above, and they will bound some region. And this region is exactly what my module is. So, okay, the region they bound, hopefully you see, is this 2 squares, 4 and 2, and this is going to give me a module plus 4. So I think of these will give me dimensions of my module with a pre-projective algebra. So this is my U sub 5. It's a direct sum of 2 modules in this case. Simple in 2 and then simple in 4. And so something to note, these U sub i's are generally not indecomposable. This is part of the difficulty. And Ui and Uj's may have repeated summons. So Ui, J may have repeated summons. So summons may repeat. Okay, so what I told you is start with the reduced expression. Each of these indices gives me a module, which is not necessarily indecomposable, but there's a way to get there. And then my module UVW is a direct sum of all these. So I should have written that. So my UVW is actually a direct sum of all of these y's. And, okay, good. So just to give you maybe yeah. So in our example, if I look at this W basic, so I remove repeated signs, if I do all the calculations, the modules I get 1, 2, 2, 3, 4, 1, 2, 2, 4, 1, 2, 4, 4, 2, 4, and 2, 4, and then 2. And now remember, if you want to know the quiver of the seed, then you have to take the endomorphism problem with this. This object. Okay, so this means you want to look at all the irreducible morphisms between the modules here, and well, this would be your quiver. So a priori, one of the difficulties is that, right, you don't have a very nice algorithm given a set of modules. How do you create the quiver of the endomorphous algebra? Well, you just, in examples, you pick some morphism and then you try to see whether it's irreducible or not. But you don't have like a step-by-step recipe to find one. So that's one of the difficulties. Okay, questions here? Modulo, the things I didn't tell you how to get these stuff. I will. Yeah. So in this example, so each of those, so I have 8, so I'll get 8 of these UIs, but if I actually go to the basic, I remove repeated summons, the number will be always the length of W minus the length of E. So kind of this is not going to give me anything in some sense. The underlined things coming from the underlined words don't give me anything. Okay, so then I want to tell you about now Ingermanson's construction. So very different. So Ingermanson's construction is very combinatorial. And so here, what you do is you start with, again, B less than or equal to W, choice of a reduced expression of W. So here you want W to be peak, and I write it here so I don't forget. And I'll explain you in a second what that means. And what you do is you create what's called a double wiring diagram out of here. Okay, so let's do an example. Okay, so this is the same W I had for Leclerc, but I'm going to explain to you how to construct this double wiring diagram. So first you start with the usual wiring diagram, and so many of you may be familiar with. So I start with 5 strands, because I think of it as words inside of S5. And I'm going to introduce crossings according to my word W. So remember, this is 1, 2, 3, 4, 5, 6, 7, 8. And so I look at the first crossing, this is S3. S3 is the transposition, this changes 3 and 4, so I'm going to introduce a crossing here between strands at heights 3 and 4, and then the next one's 2 and 1, so my crossings are 2 and 1, and then 4, 3, 2, so I have 4, 3, 2, and then a crossing in heights 3 and 4. Okay, so that's the usual wiring diagram. Just label 3, 4, 5, 6, 7, 8. And then what happens is we also have this information of B. And what I do is I overlay the diagram of B on top of this. And so my crossing B just is S3, so I'm just going to see the crossing 7. So at crossing 7, and my diagram for me, I'm going to draw in dotted lines, it's just going to have this crossing, and everything else is going to go straight. So these will go straight. And straight, everything else is straight. And one more straight, please. Okay. And so once I have that, what I can do is I have this, so every index, I get what's called the chamber minor. And that's denoted by delta I. Okay. And what is it? I can read it off from the diagram. Again, it's going to be, it's going to have, so I'm going to put an Ingermanson up top to remind you that it comes from Ingermanson construction. And then it's going to be, again, determined by two subsets, R and T. And these you can read off easily from the diagram. So the R is the labels of strands, W strands, no, the first one should be E strands. These strands below the chamber. And this is the key is the same, it's just the labels of W strands. Below the chamber. And I'm showing you an example. So in my wiring diagram example, let's say I want to look at the chamber 5. So I look at the crossing 5, and the chamber is just a closed, potentially open chamber in the diagram W. So in the black strands, solid strands, exactly to the left of 5. So this is my chamber 5. And then I'm going to put here this delta. And which delta would it be? I'm going to use a different color. Okay, which delta would it be? So first I look at the dotted strands below my diagram, and so I have this strand, I have this strand, and I have this strand. They have labels 1, 2, 3. And then I'm going to look at the solid strands below my diagram. So I have this strand, which has label 2. I have this strand, which has label 1. I also have this strand, which has label 4. So this is 1, 2, 4. Okay, so that's my minor. And actually, okay, finally I'll tell you how to get Leclerc's. Leclerc's labels. So actually, if instead you use the same rule, but instead of using the left endpoint, you were to use right endpoint, what you get is you get Leclerc's label for the same index. So for the 5, in my first example, hopefully, if you look at the same strands, but you look at their right endpoints, you would be able to recover these sets 1, 2, 4, and 1, 5, 7. Okay, so that's how they are related, but the problem is these minors, that's why I put superscripts on them, Ingermanson versus Leclerc. Leclerc and Ingermanson, they parameterize their Richardson varieties differently. One quotients by the upper triangular matrices on the left, the other one on the right. So they are really, you can't just compare them on the nose, they are really different things. They look like they have the same structure, but they're really different as functions. Okay, and very lastly, so I tell you how to get here the combinatorics, and the very last bit, let me tell you how to get the quiver, the seed of Ingerman's. Okay, so Ingerman's seed. So the cluster variables they correspond to irreducible factors of these things, of these chamber minors. Okay, so the problem is, so it's very nice and easy to calculate these from the wiring diagram, but actually in order to factor them is very complicated. So she gives a recipe and you can do it from the wiring diagram, but it's actually quite involved. So on Leclerc's side, it's nice to factor these modules because they're just lattice paths, and when they meet, they will give you a direct sum, versus here it's quite difficult. And on the quiver, is obtained as follows. So it's kind of in two steps. So first there is a quiver of the wiring diagram. So the wiring diagram quiver. So vertices of the wiring diagram correspond to these chamber minors. And then the arrows you can read off. So in the wiring diagram, whenever you have a crossing, you get arrows in the quiver, which look like, let's say, do this. You get these arrows between the associated vertices. So that's easy. So that's for the wiring diagram. And now quiver of the seed is, okay, so quiver of the seed is slightly involved. So again, the vertices, as before, they should be the irreducible factors. For every chamber minor, you factor it and you take all the irreducible factors, that's your vertices. And now arrows in the wiring diagram induce arrows in the cluster. So whenever you have an arrow in the wiring diagram, so delta I, some delta J, this gives you a lot of arrows of the quiver where you get an arrow from some delta to delta prime whenever delta divides delta I and delta prime divides delta J. So this arrow in the wiring diagram, you factor the delta I completely, you factor the delta J completely, and for every pair of factors inside of here and here, you get an arrow in the associated quiver. And so there's lots of them cancellations. You may potentially get loops in 2 cycles, but for the cluster algebra theory, remove all the loops in 2 cycles and try to see what's left. So there's a lot of redundancy here. So many cancellations happen. You kind of need to take care of that. So that's the difficulty. But at least it gives you a sort of a combinatorial interpretation what the quiver should be. And so the way our proof goes, well, we try to analyze both construction, we try to compare them and see that they actually give you the same quivers, and you can compare the cluster variables and they also kind of correspond well to one another. But it involves a lot of sort of analysis and a lot of induction. And so whatever is easy on one side, usually is very difficult on the other side. And so really think of these two as being complementary constructions. Okay, and I'll stop here. Thank you.
Any questions for Khrystyna? Yeah.
So you mentioned at the beginning braid variety. So what's its definition?
Well, the braid variety?
This is the easy thing.
I don't think it's very easy, and I'm not prepared to talk about that. I just know it as a generalization of this story.
Khrystyna supported too, isn't it?
I know it's an homomorphism, but I don't remember where to order to.
It's also
Oh, I think, so this might have been addressed in the one of the braid varieties paper. That maybe the twist step is related to something like a maximum green sequence or a green red to green sequence.
To what extent does this story extend into other thinking types, like other thinking types, Richardson, varieties, other density cluster structures and things?
That's an excellent question. So the categorical side, which Leclerc and Menard did, this is for ADE types, so that's very nice. The combinatorics of wiring diagrams only works in type A, as you know it. It'd be nice to extend it. And then also get sort of a combinatorial interpretation of Leclerc's construction. Because that's another application of this, is how to get this combinatorial interpretation of this categorical construction. So that would be something good to do.
Thanks. Any more questions or questions from online? Thanks, Khrystyna. Next will be a